So welcome back. Is anybody listening? The next topic which we would like to have an overview of are the changes of the geomagnetic field. Everybody is working on the changes of the geomagnetic field in different ways, with different resolutions, and it are these changes which, study of these changes, which give us the idea of what exactly is going on, because different processes affect the changes of the geomagnetic field, and while we study them, we study the processes. And that's what we are all doing in with different kinds of data. And we just talked about them a little bit. There's also a slide I borrowed from David's lectures because it shows everything so well. And this is the standard we know that the spectrum of geomagnetic field variations over time, temporal variations. And the different sources produce overlapping signals, yes, and there are also signals which are quite distinct from each other and cannot be confused. So the long-term changes, reversals, and this will, I think, be discussed in a lot of detail by Johannes tomorrow. So we will talk about the long-term changes and how they are.
Just a second. I will.
Sure. How they are tracked, modeled, things like that. So we know that the geomagnetic field has reversed, but what exactly does that mean? And how do we look at reversals now with so much of data and so much of understanding of the processes which are going on? But there are secular variations which may happen over a few years, over decades, or a little bit more. Solar secular changes, the sun's magnetic field changes, and that affects the Earth's magnetic field also. The solar cycle, jerks, which are rates of changes in the rate of secular variations, solar and lunar effects, tidal effects. SQ are the solar quiet variations, which are linked to solar cycles, to tidal effects, and others. Storms, and which are also linked to the solar cycles, and pulsations. So I myself work a little bit on tidal effects, on solar cycle changes, on what is not written here are seasonal and annual changes, and the dump storms and pulsations. This topic, I think, will be taken up by Jim Johnson the day after tomorrow. And so I'd just like to give some examples of these changes over time. So this is a very standard spectrum of changes: reversal, secular, solar rotation, daily variation. This is something which I've been working on a little bit for quite some time. When we talk of daily variations, we would like to see the variations on days which are quiet and days where the magnetic field is disturbed by the sun's magnetic field and Schumann resonances, etc. So in other way, we have secular variations which are long term, and they do not or may not the degree to which the geomagnetic field recovers from a secular variation is, I think, an interesting point of study, at least for me. So once a secular variation has happened, and once we feel that this variation has come to an end, then what happens to the field, and what happens to it at different places and times? Transient variations are complex and yet in some ways simple, in that once the transient variation is over, the geomagnetic field has come back to its original values and position. We see it all the time in our magnetograms, daily magnetograms, the positive emitted data, the emitted data. And these transient variations can happen on the quiet magnetic field, which is primarily on that of the core field. And we see changes in the SQ, the lunar, and tides and things included here. And we also see the transient variations on disturbed days. There are the storms, the substorms, and which changes the magnetic field. And there are also the effect of the storms. We see the different kinds of positions, and they occur in different ways and for different time periods. And then they stop, and when the next storm happens, we see them once more. So this is also something which I will not go into detail because it will be covered in today's talk, I think. So we will have some discussions on these quiet variations as well as some long-term variations of disturbed days also. So so this was a study I done some time ago from our own data, Hyderabad. So we have the idea that the solar cycle affects the effects of the solar cycle on our geomagnetic field are quite simple, and they reflect the solar cycle is reflected by RZ, which are the sunspot numbers. And this is AP, the black one, which represents the overall, it's the index, which affects the overall state of the magnetosphere. And this, we did the study over 3 solar cycles, 21, 22, and 23, and part of 23. So when we plot the data from the quiet time variation of the changes in Hyderabad, we see that there is an overall change in the solar quiet magnetic field, but it is not as prominent as the changes in the solar cycle. The rate of change of the field also, and the rate of change of the sunspot numbers and the rate of change of the quiet magnetic field were quite different. So I will not go into the details of the process. Then we tried to look at the different solar parameters and try to see which of these parameters had a better influence or a better correlation with the changes of the magnetic field, other than the sunspots. So here is AB. Here is the data from Hyderabad, the low magnitude station. This is M is ion density, BZ. This is the velocity of the solar wind, and RZ is the number of solar sunspots. So here we look at periods of 10 to 30, and we see that here we did a wavelet analysis of these time series, and what we found are we have in the long term, in the 200 and 250 days, we have a good correlation with the solar sunspot numbers here and in AP and also in Hyderabad data. But we also have influences of the ion density, and also, we don't have, in fact, we don't have that much of influence on BZ, but we also have influence of the speed of the solar wind in the data. We see that the speed seems to be better reflected in the data in Hyderabad than the sunspot numbers. And when we go to longer periods, we have a better reflection of, we have an even better reflection of the changes of ion density and the AP, as well as the data at Hyderabad. Here we see some of changes which are maybe partly due to changes in VZ or velocity of the solar wind, or well, I'm not very sure where this has come from in Hyderabad data. So what we were interested to see here that the solar cycle changes of the magnetic field have several components to it, other than just the sunspots, which we take as the standard of looking at the activity from the sun. So somebody who was working in the hemispheric field may have. Do you want to say something more on this? Whether you were working on the effects of the sun's magnetic field on the Earth?
I'm actually looking at a very specific events, the eruptions itself.
Okay.
And they occur more frequently during the maximum of the cycle,
Or
the
assembly.
peak of the number of hotspots also.
Right.
But I don't know the specifics on these measurements.
Okay, these are all general, measurements which are available from our solar observation satellites, and yeah, this is what we found. So after this, I was interested in looking at the effect of the changes in the what we have from the sun in our data, and this is one example that I would like to share from our last solar cycle, 24. So again, the quiet time variation. So these are the sunspot numbers for each year, and 2014 was, as per record, is the highest sunspot number. Although we know that, I think we are all aware that 2015 was a very active year. We had 15 major storms recorded in our data. So this was already something to think about, where the sunspots were 2014 were largest in number, but the activity in the geomagnetic field seemed to be much higher in 2015 and then came down again in 2016. So this is very recent phenomenon, and we all remember it. And when we see the number of quiet days, there is an inverse relationship, but there seems to be that lag, that change. When the sunspot numbers are highest and then it comes down, you would expect it to follow the trend, but there is some change in here. So again, I think I will just come back to the original earlier slide and say that it's not just the numbers, but there are also, we need to look at the ion densities and the solar wind speeds, which are during each storm, and then we would be able to explain this pattern of the quiet days a little bit better. So, this is data of again quiet days in a low latitude, northern hemisphere. This is equatorial, just along the equatorial dip equator, and this is another quantitative station, which is in the southern hemisphere. And I just wanted to show, there is a little bit of data gap here in two places, that there is a variation. SE is the solar equinox, and we see the 4 seasons here. And these are for one solar cycle. This is for 2012, 14. It's not a full solar cycle, but what we see is an increase in the equinox solstice, and slightly after the autumnal equinox, we see an increase again. And this same pattern is continuing. But this pattern is much more prominent at the equatorial station. And although the amplitude is of this pattern is less again compared to the equatorial station at the southern hemisphere, but the pattern is clearer in the southern hemisphere somehow. So later on, we have gone on to check the patterns of the movement of the SQ foci and try to correlate it with these patterns. And we do see that there are both an annual and a seasonal pattern in the changes of the solar quiet current or the diurnal variation. And but it is not exactly the same at all places. If we change this to another low latitude station, again the pattern is similar, but while we go further north, although it is still a low latitude station, but the rate of change and the pattern is different again. Unfortunately, in the southern, all the three stations are along the same longitude. In the southern hemisphere, there are less number of observatories from which we can get conjugate data. So we are finding it a little bit hard to continue to do the study with ground data. So right now we are in the process of using satellite data to see whether we can get average profiles of these changes every year, say for a couple of solar cycles, and I hope that we will be able to finish this work by the end of this year. So right now we are working with CHAM-A data to get these profiles. So this is for quiet times, and there is a recent paper. Some of you might have seen it, by Franco et al. 2021, where they have done a study on a very large data set, solar cycles 2021, 22, 23, and 24, so 50 years of data, a little bit more. And they have tried to look at the patterns of changes for disturbed days. When we were looking for quiet days, they have tried to do the study for disturbed days, and you will see that they have 20, 21, 22, 23, and 24 here, and the months are here, and the solar, this shows that changes in the solar cycle, sunspot number patterns. So this is what is happening, and when you look at the average picture again, you definitely see that except for 22, which seems to be this early peak seems to be definitely there's a more than 1 year's delay or lag in this peak, but the others do follow that there is an increase in the number of these are the increase in the number of moderate storms. Some of you are working on storms. So during March, and again a further one during say October or November. And in between, the number of moderate storms were lesser. So even this seems to be odd as to why there should be a change in the number of storms which affect the geomagnetic field, which may have a seasonal pattern. But this has been very carefully curated data, and this is what we see. And the substorms show the same pattern. Very similar pattern, and here even SC22 have the same pattern. Here they don't have the data from the solar cycle 20. So this is a very interesting observation, which could happen because data was available for 50 years, and this is still based on ground observatory data. But I think we are also working on looking at it from satellite data. And what they also found was that they did not find this pattern yet for intense or superstorms. Either because there were lesser number of superstorms to record, so we need longer data series to show whether, to really establish whether this pattern exists for the larger storms or not, or because the intense storms actually do not follow this pattern. So people are still working on more data to see, and in solar cycle 25 have lots of storms. So maybe with the end of the solar cycle, we have enough data to see whether bit larger, more intense storms also follow similar pattern or not. But right now, even the disturbed days seem to follow seasonal pattern, which is very interesting, and there's the need to model why this may be happening, because the sun should not be following the Earth seasons, but the way the Earth's magnetic field is affected by the solar magnetic field changes seem to follow this pattern. So these were two examples of changes in solar cycle and seasons. And of course, I want to share with you an example of secular variation studies as well as charts. And this is again from data for the Indian observatories. And we have one observatory in the north, and the distribution of observatories over the country is uneven. We have observatories here, but data was too noisy. There were too many discontinuities in the data, and it was not possible to use it for this analysis. But we have one observatory in the north, and rest are all low latitude observatory, and this last one is in the equatorial region, although the magnetic equator has been shifting over time. And we see that the horizontal fields, X and Y, follow the similar pattern of decreasing over time, whereas the vertical field is increasing over time. But in the low latitude, near equatorial stations, we see an increase in the x-axis in the recent years of this is from say 2015 onward or 2012 onward, whereas in the y-axis we don't see that yet. Z has been similar throughout and has shown an increasing trend throughout the space. So I have not gone through how you come to this, whether you take only the nighttime data or nighttime data from 10 p.m. to early morning local time, and people work in different ways to extract these changes, but we have tried to see this just by taking all the annual means, then by annual means of the quiet days. We have, and the pattern is very similar. There may be a little bit of changes in amplitudes, but there's no changes in the pattern at all. So then we try to look at the rate of change of the secular variations, and this also has an interesting pattern. The lowermost panel shows the changes in the Z component of all the different observatories. This one shows the changes in declination, and this one shows the changes in the horizontal component. And what we see here, this is the northernmost station, and then these are the regular and middle latitude stations, and the last three are the low latitude stations, near equatorial latitude stations. So here we have, we see, we do not have data to the end, so till the time we have data, this is more or less the same at the north and in the middle latitudes, or low latitudes actually. But the D, the changes in the declination are definitely quite different. And we see a large change in the declination in the low latitudes. And we also have, when we look at the Z patterns, rate of change in the Z, we have more or less similar patterns till the time we have data here. When we come to the lowest near equatorial stations, the pattern is somewhat different from this station, which is very near the coast. So we are checking for the effect of the coastal effect on the circular variation changes, and but somehow this observatory has shown this kind of change compared to the others. We see that the rate of change in the H component remains similar, except in this is Hyderabad. Yes, it has started to come down, but here we don't see the change because we do not have enough data. The D rate of change in D component remains the same, and in the near equatorial regions, in one station we see a recovery again of the circular variation rate of change. It becomes positive again, whereas the others it has been only going downward. And from this, we try to look at the shift of the magnetic equator in this region of the eastern longitudes. And when we look at the magnetic equator in the 1960s till the 2018, we see that it has moved from 8.5 degree geographic latitude to now about 6.5, so it's already moved about 200 kilometers further south. And this has been recorded by others also earlier, and it has been recorded in other parts of the world. It has shown a sinusoidal change in the position of the magnetic equator. Means in Africa, for example, and in South America, we've seen that it moves to the south and comes back to the north and moves again to the south. And however, so far it was due to have moved back north, but so far hasn't. So I don't have any explanation of this, which will involve more modeling of the field, but the current model resolutions that we have do not yet explain the changes of for example, the equator longitude-wise. They trace much larger features of the field. However, this is not yet this feature is not yet modeled, so we hope that with more years of satellite data, it will be possible to model what are the changes in the core field which is sustaining the further downward movement of the equator in these longitudes. So far, is there any point you would like to add, or?
I have a simple question. What is exactly meant with the dip equator?
Okay. Dip equator is the location around the globe where the dip is, the inclination is zero.
The inclination is zero.
Yeah. So you get the positive north and the negative south. This is seen in the GRF and all the models that we will have. So now you can recall the figure of the dip equator. I'm sorry that I should have probably put a figure on this, but I thought it was very familiar to everybody and I didn't include it. So like the geographic equator is one great circle, but the magnetic equator is not a circle.
Yeah, so it's without fitting a dipole to the field.
Yes.
It's really where the inclination is zero. Yeah.
And
there is a feature of the equator.
yeah.
It's not magnetic.
No,
It's not the most of the data, but
Yeah. Okay.
Okay.
Yeah, so it's irregular.
Yeah, it is on some particular year and the duty equator there is coming further down. So maybe it becomes like this later on, like the duty equator near the South Atlantic anomaly. With time. We don't know yet.
I was just wondering, is it always unique, like one bit, or can you have also some more minimum by one fluctuation?
I think that's the question.
So you define the equator by a minimum, but in the minima due to some local, fluctuation or some variation, that you will have not one bit, but two points.
Two locations where the bit is zero. Actually, it depends on what we mean by location. How close are the two positions where we measure the dip zero? And in reality, it will not be one point. If we measure the dip zero at this point, even here, with our current instruments, it will still be zero. So yeah, it's a little bit of a region, say.
The reason
Is that
I'm
the
asking is that when we are like a far away from Earth, getting close to the intervals, then we typically have like few minima. So I was wondering if close to the Earth, some deviations from dipoles that are very strong, and maybe because it would be sometimes with like few minima, two equators that would be separated by some reasonable margin.
Yeah, that's a very interesting and open-ended question, I think. When we measure, when the primarily dipolar nature of the magnetic Earth's magnetic field changes into more than two poles, then definitely that's what's going to happen. So we're waiting to see whether that's what's going to happen.
So in terms of the biannual variation, so yeah, there's an auroral phenomenon that also exhibits the same thing, and I looked it up. It's called the Russell-Mc-Ferran effect.
Yes.
Is this, I guess, related probably?
Yes.
Yeah.
Definitely, it's related. What was your first question? What was your original question?
Did I have a first? I'm sorry, I don't follow. I was just asking if it's related to.
Yeah. I mean, that's how it is explained and it will be modeled. But we need enough modeling at that scale to be able to actually fit it. Okay, so if something is happening along the entire dip equator, then that's something we are able to model. Is that what you're talking about? You're talking about the seasonal changes earlier.
Yeah, so in the autumn and in the spring,
Yes. Yeah.
there's significantly higher substorm activity.
Yes.
Yeah.
And moderate storm activity. So if the physics holds, it should be there even for the larger storms or the more intense storms, but we have not yet found that pattern. Maybe because we need more data to look at it.
Maybe I'm just getting really excited about what's coming next, and then what's coming up that we just sounds good. But I don't see. I struggle to comprehend how the moon can affect geomagnetic field variation over time.
No,
That's cool.
yeah. It is a very small amplitude effect. It's something we are working on right now, and many people have worked on actually. When we talk of the tidal effects, now I have not included a lot of material on tidal effects. We have the solar tidal effect on the Earth's magnetic field, and we have the lunar tidal effect on the Earth's magnetic field. The solar tidal effect is primarily a thermal forcing, and it is a forcing from below. So it is the heating of the atmosphere which will give rise to waves, say acoustic gravity waves, which will make changes in the magnetic field. Because it will change the concentration of the ions in the atmosphere. And that's something we record in the ground stations, right? And we also record it in the satellite data. So if we have contemporaneous ground and satellite data, it's possible to identify it much better because the satellites will be recorded with higher amplitudes. For the lunar, it's the changes in the gravitational effect of the moon, which again gives rise to changes in the Earth's magnetic field. This may look.
It's the movement of the ocean, isn't it?
Yes, yes.
The moon is moving the ocean.
Yeah, right.
The ocean,
Yeah. Conductive water.
They have this overflow of conductive material through the main magnetic field, and so that induces the electric currents in the ocean. And so then that induced currents in the ocean get their own magnetic field that adds to the energy that.
These are very amplitude-wise. They are like few nanotesla.
So actually, it's kind of the opposite, where you're saying that you get higher amplitude from solar tidal and satellite, but then with the lunar tidal effect, you get higher amplitude from ground.
Yeah.
Cool.
With currently we are looking at this only from ground data, but with the solar, we are also trying to look at it from satellite data and see what the difference between satellite and ground data can show. But a lot of work has been done by tidal effects. And then how the tidal effects are slightly different in different parts. It will also depend on where the observation point is. It's not going to be exactly the same. For the amplitude of the tidal effect is going to vary depending on where we are measuring it.
Do you get lunar tidal effects? Say if you have an observer essentially slap bang in the United States of America, no oceans nearby, well then there will be a smaller effect, assuming you
Yes.
have up the coast.
Yes. So that's it. This is our new solar cycle 25, which has turned out to be much more intense than it was predicted. The prediction based on the last 4 solar cycles was that it's going to be even whiter, but it has not. And we have disturbances in our netometer data every day. And even a couple of days ago, we were having a storm going on. Activity in the field, not a major storm, and then solar flares almost every week. And this solar cycle, the data from this solar cycle is going to prove very crucial information, going to provide very crucial information as to what is going on in the magnetosphere and the changes that we are observing and the way we can model them when we see the changes for the last 5 solar cycles. Comments, questions?
So I was just wondering whether, so with really, really big substorms, I'm not sure, because the Russell-McLaren effect, I think, is because the magnetic pole is pointing towards or away from the sun, so there's worse coupling at, in winter or summer.
Yes.
So surely, if the substorm is, if the activity is high enough, then the substorm will just be so big that it doesn't matter how much coupling there is, it will just always produce a massive substorm.
Oh, I'm not sure I can explain the mechanism. And it also changes when you take observations of observatories from again the southern and the northern hemispheres a little bit. That particular study by Frank Portal was based again on observatories from the northern hemisphere. So the data was from which the substorms were identified were all from the northern hemisphere. So he has taken all the substorms when he made that pattern, and even the moderate ones and the larger ones. And for all of them, he found the similar pattern of the Russell effect. And what we are also interested in seeing is how the substorm has affected changes in the equatorial regions also. That is a work in progress. But there should be an effect of these substorm wedges on the low latitude and equatorial regions where we can expect to see there. Then a little bit later after the substorm is identified in the polar region.
I was just wondering if you know the slide where you show the number of days for taking index by 23. Did you find a similar pattern for a certain year in other previous cycles, or is that checked anywhere?
Yes, when I showed the first slide, where we had the pattern for the solar cycles 20, 21, and 23, it was again a very similar pattern.
So after the maximum, there would be like 1 year with less 5 days, even though the maximum is over.
Oh, that is, I should say yes, but with conditions, because in solar cycle 24, the number of storms or substorms in the year 2014, the year 2015, and the year 2016, if we just take these three, were very distinct. But for every solar cycle, we may not have exactly the same pattern. In some solar cycles, even in the maximum years, 2 years may be more similar to each other. Okay, so the solar cycle during their ascending phases, the maxima and the descending phase, are not exactly the same when you match them to the number of sunspots.
Yeah, no, I was just thinking because obviously solar cycle 24 was the kind of very special, as you can see even over here. So that's why.
No, but even in solar cycle 20, 21, and 23, we have seen a lag between the number of solar sunspots which were identified and the activity in the magnetosphere or the geomagnetic field. And that is what led us to investigate what may be the other parameters other than sunspot numbers that we can look at.
No, of course, I think like the corona holes where the high-speed streams are originated and also have a huge influence, not just like the eruptions itself. So, as you said, the pressure and the density and the speed that
Yes, exactly.
So
So we need to plot all of that, and then we see that what we see, the pattern that we see in the geomagnetic field is actually a superposition of all these effects. And sometimes one effect is stronger. For example, there were several times when we realized that the effect of the ion density changes are more than the changes in the number of sunspots. That was more prominent or more dominant than the number of changes in the number of sunspots. I mean, there are many examples of seasonal and solar cycle changes. For example, right now we just completed a work on this change seasonal patterns of the equatorial electric jet, like we have done with the polar electric jet of the substorm. I mean, we can go on with many examples, but the main point is that for quiet times as well as for storm times, we see a clear seasonal pattern, and we also see a solar cycle pattern. And yet it's not a one-on-one. There are several parameters which is affecting the overall pattern of changes. Yeah. Was there a question? Yeah.
It was just when you were talking about, so my research is genetic effects.
Mhm.
And 2019 Indian that's really annoying because there were really big ones in the Pacific, 2017 and 2020, and if they're only those 17 would be really nice to see this great. But I was wondering, your data went up to like 22.
Yes.
Is there going to be 23?
Yes.
Soon.
Yes. Soon. Yes.
That would be great. 2017 in the Pacific and nothing elsewhere. And then in India and in the Indian Ocean, you have 2017, 2019 and 2021.
Yes.
So, really interesting.
Yeah. So hopefully, Jay will talk, or Johannes will talk about how how models are going to explain what is happening in the core field, which will explain the different, again, the time differences in the observations of the germs in the different cases. Or maybe you will explain this. So, is it all?
That's another
Should we start with the model, actually?
Standard approach. Yeah.
Or- So, we just, look at the concepts of modeling the genetic field. So the first, okay, so what are these models? So the most common or the model of the genetic field that we all learn in school is that of a dipole. But the Earth's magnetic field is a dipole. That's our first school understanding of the Earth's magnetic field, that there are two poles and where the magnetic fields are strong, and then in the central part it is the weak part. And actually, for a lot of things, this dipole model works, but not when people who want to do research on the genetic field. For them, this dipole model is not enough. So it's a first order. It was a first order approximation, yes, but insufficient to describe the changes of the genetic field from place to place and in time. And we have seen examples of that in the earlier presentations. So so a lot of work again has been done as he's working on to represent the core field and its variations, and use all the data from observatories, from satellite and aeromagnetic surveys to derive these models. And these models should make it possible to predict the trajectories of charged particles, mapping of field lines. The more accurate the model, the better will be the prediction. So, yeah. So all the components of the geomagnetic field that we know of contribute, have to be reflected or contribute to the models. The main field from the Earth's core, the secular variations, which means the changes in the main field of the Earth's core, which vary the time and the location. The lithospheric field caused by magnetized crustal rocks, the motional induction in the oceans, as Ashley was explaining that the conducting waters of the oceans contribute their own field to the overall measurements. Tsunami-generated magnetic fields occur in theory, yes, but there are not so many tsunamis. Anospheric field is very important. It changes all the time, and it changes from the equatorial region, low latitude, high latitude, all over. And so atmospheric fields are a very important contribution to the model, and changes much more frequently. The changes of these contributing components are different. And magnetospheric fields also contribute to the model. So the models have to incorporate data and be able to explain the changes in each of these components. The percentage of contribution of each of these components and the patterns of changes of each of these components. So this is something that a lot of work is being done on, but there is a lot of more interesting things to go with, because each model has their strengths and their weaknesses. Explain some things, and there are some things which remain to be explained. So there is more and more work to do to use more data and get more accurate models. So the basis of starting to model the geomagnetic field was Laplace's equation, where in a region far from the source, we can apply the Ampere's law, and when we also apply the Gauss's law, we have this simple equation of the geomagnetic field, which is where V follows the Laplace's, satisfies the Laplace's equations. And this allowed the concept of spherical harmonic analysis to be applied to the analysis of the geomagnetic field. So I think most everybody here has studied spherical harmonic analysis in school, in our schools, and we have the standard expression for the potential of the geomagnetic field with M as degree and N as order and surface harmonic. So the spherical harmonics are able to represent the geomagnetic field over a spherical surface, that is over the Earth, and the associated Legendre functions are expressed in this form, and for the geomagnetic field we use much quasi-normalized form of the associated with the Legendre functions. So for internal sources, we use where we have the radius here r, which is less than the radius of the Earth. So we use this expression, and when we want to look at, when we want to model the geomagnetic field in the ionosphere and in the mesosphere, then r is greater than a, so it's beyond the radius of the Earth. And here, the idea is to be able to compute the Gauss's coefficients, and just not based on the data that we collect, and then with once the Gauss's coefficients are computed, we can use them again to get a computation of the field at another point. So when we break it from the total potential, we can use this for each of the components of the geomagnetic field, the x, the y, and the z, and we are related to the geomagnetic potential by these relationships, and we can apply the spherical harmonic analysis for each of these components, which is what we do now, and we can either make the model of the entire potential, or we can try to make a model of each of these components. So, what do they look like? Their spherical harmonics are orthogonal functions. The Laplace series is infinite, but depending on the data we have, the number of data points, the distribution of the data points, we will decide where to truncate the infinite series. The coefficients of the spherical harmonic functions are determined by least square analysis after truncating the harmonic series at some degree of error. And I think in the tutorials you will be able to see how when you include more data, you will reach higher orders and degrees, and with this data is we have to move only to lower orders and degrees. And inverse methods are applied to retrieve the field at a point once the process coefficients are calculated. Each harmonic is equivalent to a particular arrangement of magnetic charges at the center of the Earth. So we have already come to the concept of a field which is not completely bipolar. Spherical harmonics, so we become or express the geomagnetic field as functions of latitude and longitude. And this is how we see when for n is 0 and n is 0, we get a dipolar field. But once we increase the order of n and n, then we can see the different. We can represent the changes in the geomagnetic field with more and more details. So with spherical harmonic degrees, increasing degrees, we should be able to, when we include larger harmonic degrees of n, then what happens is that we have more and more superposed effects of the different components which contribute to the field. We have the field-aligned currents, high latitude currents, low latitude currents. So with more data and when we are able to express or represent the model of the geomagnetic field, which will vary more rapidly with time, we also should be able to represent these changes which we see in the observations. So the changes in the model and the changes of the observation have to be matched. And they match at some time. I mean, of course, overall they match, but there are details which where still there are lots of mismatch which needs to be recomputed. Coefficients can be recomputed with more data and get a better match and so forth. So this is the altitude representation of each of these effects. So some of these are very near, close to the core field, for example, and some of these are further away in distance, and they all have to be brought again. You see in the tutorial that what does the model look like at 400 kilometers from the Earth's surface, at the Earth's surface, and then even in the subsurface, say at the core mountain mantle boundaries. So people who are working in this area, they know that you are able to model what the geomagnetic field looks like at the core mantle boundary, at the surface, and then in the atmosphere or magnetosphere. So this is just a depiction of when we are farther away from the source and we have less data, then we have a more averaged picture, and the closer we are and the increasing number of data points, we are able to explain more details or represent more details in our model. Next explanation, this is how we see more and more details when we are closer to our source and when we have larger number of data points. So from a long time, it has been extremely important to develop models of the Earth's magnetic field. The map that I had shown earlier, the world magnetic map, pure magnetic model and the enhanced magnetic model, high definition geomagnetic model. These are, they have very large degree and order, 790, and spatial resolution of 51 kilometers. So they represent the changes at every 51 kilometers on the surface of the Earth. And they were required and are still being used by, airplanes and all navigation systems, actually. And the way we find our cell phones find their way to a place, or it depends on these high definition geomagnetic models, which are used primarily for navigations. For research models, another flagship product is the IGRF. Everybody uses IGRF, I think, in some form or other. And this is has been developed, I think, from 1960s. 65 was the first IGRF, and this is based on collating all data from observatories, and now IGRF includes data from satellites, and which gave a very homogeneous coverage of the magnetic field of the entire Earth. And then there is the KO series and COB, which is from observatories, the CM series, and there is the core flow model. And these are also available up to degree and order, very high degree and order, 790, and a high spatial resolution. The IGRF has, the original one was degree and order 12, but now IGRF 13 has brought us up to degree and order 13, which is the most recent version of IGRF.
Just a small correction on chaos. Chaos is like GPU and degree and order are
Less. Okay. So there are, the IGRF describes the internal part of the Earth's magnetic field, and is of course used by all scientists. The latest version is IGRF, which was released a few years ago, and the IGRF also includes from 2015 onward a linear predicted secular variation model, which which predicts how the different components of the geomagnetic field will change in every 5 years. And this is available up to degree and order 8. And then you have lithospheric field models. So how the lithospheric field models are generated, are computed, is also different for different models. There's the Green series model, which are still available, which are used by many. There's the LCS model, the model from the Chinese, the seismo-electromagnetic satellite, which is relatively a recent satellite, so it has just 4 or 5 years of data, and the NF series models. These are available up to degree and order 42. It was released, I think, earlier this year, this model, and NF series is up to degree and order 133. So, and then why are there so many models, and how do they differ? So I'm not computing models, but all of us use these models to remove some effects that we would like to remove from, especially when we try to use satellite data. So if you use CHEM data for 1 or 2 or 5 years, then it includes all of the effects of all of the core field, lithospheric field, and all of these for the entire Earth. So what we need to do is use a model to remove the effects of these from the data that we collected from JAMP or say SWAN, and then see what is the residual data and try to match it with ground observatory data and work on whatever we would like to work on, the atmospheric changes or magnetous pulsations or whatever. So the discrepancies between the various models are due to the differences with which the data is processed. Now, in the recent models, all the data which is included by the people who are generating these models, the scientists, are very large. So because the data collated, collation of the earlier data has already been made, and at the current time there are several satellites which are producing high resolution data in real time, and all of these are included to produce the next generation model. So each generation model has more data in it, and that's how we can arrive at higher degrees and orders of the models. And however, how we select the data, how we select the magnetically wide periods, and how we estimate the spectral harmonic coefficients, and models also differ in how the magnetospheric and ionospheric contributions are identified. And either if we want to look at the Porphyry model, then we may wish to eliminate these contributions, or it depends on what the model is focused upon. And what, for example, the lithospheric models will not want to include the magnetospheric and ionospheric effects. Or the lithospheric model will not even want to include the Porphyry effect, for example. So that is how the models differ. It is the modeler who decides what this model is going to represent the best. And at some levels, the models will have overlaps. And at others, they will show the different components. Some will have more details on that component, for example, the lithospheric case. Others will have more details of the core flow model and its changes over time. So that's how these models differ. And once you go through the tutorials, you will have better appreciation of how the different models are changing, or how they are different at all, and how these models also are different when we use different degrees and orders and different input data. Long duration models, Jillian will talk a lot of them. These are models of over long periods of time and are based on RQ and paleomagnetic data, and either from sediments, from volcanic data, or from the last few tens of thousands of years are based primarily on archaeomagnetic data and have higher accuracy of the knowledge of the geomagnetic field evolution of the Holocene, and even it shows large-scale field changes before mountain mantle boundary as well as on the Earth's surface. So they have been able to explain, represent the expressions that we have, we know about. So these models have shown the Greenland expression, the Rashad expression is the most prominent one, and the others, and we will talk about them in more detail and how they are constructed, and what is the resolution of these long-term models. So